Okay, excellent. Well, thanks for the invite. I'm happy to be here sharing a bit of like what we are doing at Netflix. And good afternoon for everyone, or night or morning, depending on where you are. I think there's people from all around now. Well, my name is Martin. I'm a performance architect at Netflix. I've been here for almost 8 years now. When Netflix was slightly smaller, I remember actually celebrating the 15 million user party. And back then we thought, hey, we'll never reach 100 million. And I think your last quarter, I think we're at 193 right now. So we're kind of a bit bigger than that, in both team size and users. So I've been focusing on performance for almost 15 years now, I think. Most of that time really in B2C products, large scale, like Netflix. And all aspects of it. And my goal here today is to share a bit about a tool we developed at Netflix called FlameCommander, kind of our centralized cloud profiling solution. And just to give a bit of context, like when I say performance at Netflix, and what exactly does that mean? Performance of what exactly? Of the product. So, and for us, that is something fairly simple. Is the actual streaming service that some of you might know. And all that is necessary to make that work. All the backend services, client applications, and all the technology behind it. Globally, like from the Linux kernel to the app you're running on your phone, your laptop, or TV, Blu-ray player, and whatnot. The architecture of the system as a whole, the infrastructure at AWS, or CDN that deliver all the video bits to the user devices, everything in between. Actual code and architecture optimizations, tooling for performance. And although our team is sort of performance testing falls into our responsibilities, we don't really do a lot of that anymore for kind of a few different reasons. But the focus today is like one of these tools we developed over the years called FlameCommander. And kind of the epoch where everything started for FlameCommander was about 2-3 years ago, I think, when my colleague Vadim, he had a troubleshooting issue. It was quick overview is kind of a microservice that was like suffering from some latency spikes every 15 minutes or so. No obvious cause, like changes in workload, external interference, and so on. The spikes in latency were also correlated with an increase in CPU utilization. So, usually lasted only a few seconds. Pretty common. If you're a perf engineer, you've probably seen something similar before. And also, just for context, except from the CDN, we actually run everything on AWS. And we all have root access to production, and most of our analysis actually is done there. Same applies for basically all examples I'll use today. So profiling production instances actually receiving real user traffic. And so knowing also that the issue is kind of correlated with CPU usage, our first reaction was, hey, let's just capture a CPU profile and we'll generate a flame graph, which generally helps solving this kind of issue. Assuming most of you are sort of at least familiar with flame graphs, at least probably seen one before, but in a nutshell, it is a form of visualization for profile software. The way you read it is the x-axis is not the passage of time, but the stack population, and so how frequent a stack is. And in this case, it will be sampling CPU profilers, so population will be the number of samples on CPU. And the y-axis is the actual stack. So wider the bar, more frequent stack. That's stack frame rates. So we generally look for large frames and plateaus and this sort of thing. The problem with using this approach was that it was tricky to capture the issue in a short profile, as the onset kind of kept fluctuating. So it was hard to just catch the issue when it happened. And capturing a longer profile didn't help either. As the issue is kind of washed in the normal workload of that service. Remember that the flame graph is an aggregate representation of the whole profile. So we captured a longer profile and we started slicing it, smaller bits, manually, looking for spikes in activity, and then generating the flame graphs. It did help solve the issue. We isolated the segment with the spike. So which, by the way, was the JVM recompiling a lot of code. The Groovy application, and there was a cache with a 15-minute ETL, and the cache expiration triggers some refresh of scripts that trigger a lot of recompilation. Solve the issue, but the process was really time-consuming and quite annoying. It was a simple issue, but the approach of slicing the profile looked quite promising, at least for that class of problems. But obviously, we needed a better way of getting that done. You see, flame graphs are really great, and we use them extensively in Netflix for everything. But they don't really have a time dimension, which makes troubleshooting issues like that a bit more tricky. So to help with that, we created a secondary visualization to complement all the flame graphs. So a subsecond-offset heat map, which looks a bit like this, a heat map, but is different than probably the regular heat map that you are used with the frequency, where you have a metric frequency over time. You have the time passed on the x-axis, and you have your buckets on the y-axis. On our heat map, both axes actually represent time. So each column represents a full second, so regular x-axis period of time, 1 second per column. And each cell represents a fraction of a second. So, if I have 50 rows, like each pixel or each cell in that heat map will have about 20 milliseconds of that profile. So your 1,000 millis divided by the number of rows. It's drawn like bottom to top, left to right, like a raster. The color of each cell reflects the number of events that happen within that time window. So the darker the red, more events happen. And with the secondary visualization, we created FlameScope, which is sort of a proof of concept of this idea. It's basically a web-based tool. It allows you to open the capture profile and use both visualizations to analyze it. Use the heat map to see the whole profile. Then you find interesting bits like blips of high utilization, different phases, like blocks of inactivity, and you zoom in by clicking on the heat map cells. And that will take you to a flame graph of just that small time window. Like for example, I have a cell representing 20 millis of the whole profile. If I select 10 cells, I'm zooming into 200 milliseconds of that profile. You can go back and forth between visualization, zooming into different parts of the profile you find interesting, and that's kind of how you analyze it. So this new visualization helps us solve the intermittent behavior issues a bit more easily. Same applies for other things, not just CPU profiles. You can look at memory allocation profiles, like a lot of different things that you can get stacks of. You can use this sort of visualization, get a better glimpse of the time dimension. It helps solve the issue because now we could actually capture longer profiles and just zoom into exactly what is going on parts. But as we started looking at more profiles with FlameScope, we started using more and more. Like even things we captured in the past before we actually created the tool. We started seeing some interesting patterns in those profiles, like things we didn't notice before, or things we didn't really know about the application. Things like this, single threads, waking up once a second. Like you wake up exactly at the same time once a second, do a bit of work, and that kind of causes that behavior. That's what you see in the heat map. So two threads, like waking up a second each. So they kind of bit the straight lines. Busy wait threads, those are super common. Like this thread does about 20 milliseconds of work, then sleeps for a whole second. Very common pattern, as I mentioned, it results in this kind of wake up, offset, creeping forward each second. A busy wait thread, but doing more work. So you can see the slope is higher. It's doing more work per second. Like looks like about four cells, so about 80 millis. Another busy wait thread, but this time doing less work. So the slope is a bit less. It's just doing less work per second, probably just a few millis. A busy wait thread, this time waking up twice per second. So the wake ups are like 500 millis apart. chances are it's just one thread waking up twice a second. Busy wait threads, but this time waking up every 5 seconds. You see the same slope, but you see the dots kind of spaced apart. We can also see different CPU utilization levels. This is what you would get if you kind of max out all CPUs perfectly. 50% CPU. This is like real workloads look a bit more like this, like it's composed of short requests, random arrivals, 25% CPU utilization, 5% CPU utilization. We can also see load increasing. We can see the color shade of the cells getting darker and darker as the time passes. We can see a variable load, the normal kind of 25% workload on the background, and then every 30 seconds or so, there's a 5 second of heavier work, which is like similar to the issue I've mentioned before. This one is cool, like CPU perturbations. Every so often, all CPUs max out for 100 millis. It's a pretty common pattern in Java, where the perturbations are usually garbage collection. CPU blocking. So every so often, all CPUs idle for like a few millis. Might be blocking on I/O, for example. You see those like white lines. Obviously, things are not like always that clear. Like what we usually see is something a bit more like this. It's sort of a mix of everything. Have busy threads, sleeps, blocking behavior, perturbations, load increasing. But with FlameScope, we can now like easily find those patterns, especially if you kind of train your eye to find those patterns. It is a fairly simple visualization, but it really allowed us to simplify the process of troubleshooting certain classes of issues, and identifying interesting workload patterns. FlameScope is an open source project. It's on our GitHub page. And you can use it as a standalone tool or any of its components on your own profiling applications. Feel free to clone it, test it, fork it. Send PRs. We're always kind of open to contributions. Backend is written in Python, like front end is in React. It supports a few different formats out of the box, like Linux perf, which is what we use most for sampling profile. Google Trace event format, which is used by Chrome and a bunch of other tools. So you can actually capture a profile on your browser and kind of open with FlameScope too. We support V8 Profiler. We also created a sort of an intermediary format that, for lack of a better name, we're not really creative. We call Netflix profile. So like if you plan on writing a converter, which is what we do frequently these days from whatever profile format, the definition libraries and a few converters, it's all open source. Same goes for the visualization plugins, the JavaScript DT plugins that we use on FlameScope for the flame graph and heatmap. It's all open source too. FlameScope helped us a lot, but like I mentioned, it is more of a proof of concept of this new visualization than a full-fledged profiling solution. It reads from local disk, so users had to download it. If they are not from the Python world, they had to get Python, learn how to use virtual environments, preferably, get all the dependencies and get it running. You had to get the whole React and Webpack environment going, download more dependencies if they wanted to build the client application themselves. They had to keep updating it because we have new features coming every week. And on top of that, they had to know how perf works and all the options and how to configure them, solve all the frame pointer issues, symbol mapping, and the list goes on. Let's say it wasn't the lowest barrier of entry for most engineers, especially if they never had to deal with performance issues before. And the barrier of entry is really important for us. See, we have a small performance engineering team. Let's say we have 5 engineers to deal with all sorts of performance issues end-to-end globally for all our users. So we really need ways to scale our efforts. And one way of doing that is by creating tools and having more engineers use them. So, everyone at Netflix can troubleshoot performance issues without really involving us. With that in mind, we thought, hey, why not have a centralized FlameScope? It's a lot easier for users. FlameScope is already web-based, So we just need a centralized store for the profiles and sort of a same way for users to find and analyze them. Since we might have thousands of engineers using the tool, like hundreds of thousands of profiles, and while we're at it, why not centralize the profile collection and triggering too? So we can abstract a lot of the complexities from the profilers and avoid the task of copying profiles around. And that's how FlameCommander was born. It's a centralized web-based profiling solution. It provides the same heat map to flame graph visualization as FlameScope, plus a few others, and allows capturing profiles from any of our cloud instances at a click of a button. Stores all capture profiles in a centralized location for analysis and in archival. We obviously had to make a few UI improvements to make it as intuitive as possible. We plan having a lot of people use it. And on purpose, it sort of resembles a modern web-based cloud storage UI, like your Google Drive or similar. Less the hierarchy, but with a few more filter options. You get your table of profiles and your list of actions on the top right of the table, with options to open different visualizations, like your heat map and flame graph, download it, get more details from the profiles, and so on. Pretty simple, pretty straightforward. Triggering a new profile is also pretty simple. Like you have a few options on each type of profile, but we try to abstract most of the complexity from the users, like how we deal with stack unwind, symbolization for each language we have available, how we select the right process for profiles that are not for a whole instance. On containers, we collect profiles at the host level, so we need to deal with a lot of the issues that filtering, symbol mapping, right? The architecture too, it's pretty simple. Like we reuse a lot of things from Amazon to get it rolling. I don't want to get into too many details of it, but this is sort of how it looks from a high-level perspective. Backend in Python, front in React, same as FlameScope. Once a user triggers a profile collection from the client, from the UI, we go and check if that user is actually authorized to do that. Same thing for visualizing that profile. We have an internal service that takes care of that. We want to make sure that that user has access to that service and so on. And assuming everything is okay, we generate a few necessary tokens for profile collection using Amazon's token service. The new thing to us, and worked quite well, is using Amazon Systems Manager, or SSM, to execute the actual profiling scripts on the instances. So we upload all those different profiling scripts to SSM and all the tools and everything. That's where they kept with version and tightly controlled. And we request those to be executed on specific cloud instances or multiple instances. Each instance has an SSM agent running that actually allows the script to be executed. The instance goes then downloads the asset that it needs to execute the script and installs whatever is necessary if it's not there already. From S3, executes it, creates a profile, and once it's done, it copies all the outputs back to Amazon's S3. SSM is also aware of the execution status, errors, and whatnot. And once it's done, it sends a notification that adds a message to a queue. Queue gets read by a Lambda function that processes all the raw profiler output, might be perf, might be something else, into something that can be consumed by the backend, like the binary format I mentioned earlier. It also updates the profile metadata in our database, so backend knows where the profile can be consumed. With that, the user can finally analyze in the client. Container use case is pretty similar. Like we just run a set of different set of scripts in the host that kind of isolate profiles by container, but that's sort of it. There was no large technological leap here. There was a new visualization, new profile format, but making the whole process easier is what actually made the huge difference. Abstracting a lot of the nasty profiling details, making it work out of the box, a variety of scenarios with different programming languages, that was the differentiator. Making it simple, while still providing options for more advanced analysis. I mean, the perf team also uses that. And as soon as we launched, internal user just kept growing faster and faster. A lot more work than we could have dealt with within the team. And as I mentioned, FlameCommander is probably a couple years old already, and since we launched, it grew to be our centralized profiler. Basically, keep all our profiles in there that is used by a lot of engineers. We kept adding more and more features to it, like more profiles, just things that are sort of common to developers, like heap dumps all the time, just integrated with Eclipse's memory analyzer tooling in GFA. Memory allocation profiles, where you can actually get the number and size of memory allocations. And that can be nicely visualized by the heat map and flame graph visualization too. We have different variations and options for CPU profiles, like an uninlined stacks option. Some languages inline stacks, and that makes it a bit more difficult to analyze, especially if you're comparing them. So we do uninlined flame graphs too. We started with Linux Brave and Ashtrace. I think that's the base of tools, but with time we added a few more application level profiles, like V8 profiler for Node and Java Flat Recorder for Java. Off CPU profiles, so we can analyze where time is being spent waiting while blocking on I/O, locks, timers, pagers, swapping, and we also added a few more BPF-based tools. Off CPU profiles is a BPF tool. And we recently actually added a web interface for BPF trace. If you're familiar with that, super powerful, and it helps a lot. Barrier event is a bit higher, but it does help a lot, especially if you can provide a few base scripts for users. We also invested in more analysis options, like different stack parsers for flame graphs, like reverse stack for top-down analysis. Regular flame graphs, really good for doing a bottom-up analysis, and then we have the reverse stack that's better if you're analyzing things top-down. We have package or module name parser, where kind of the package hierarchy is used instead of the stacks. Basically, if you analyze a specific package, it comes in handy, and that's just the package of the leaf node. Demango or beautifiers, whatever you want to call it, for different languages. Sometimes the frame names that come out of the profiles and the symbol mapping have sort of strange characters and information that is not super useful for analysis, and we created a lot of functions that kind of clean those frame names to make it easier to merge them in the flame graph and actually analyze. We also added more dimensions to the analysis, like breaking CPU profile by process, thread, or CPU. It comes in handy, especially if you're talking like mobile devices. In this case, we get multiple heat maps, and you can zoom into each one of them independently. Like this example here, I broken down by process, where the first process, Java, is using pretty much all CPU, and then like something weird started happening towards the end of the profile. Comparing profiles is a really common use case. So we created differential flame graphs to help with that. It's a new visualization. It to simplify comparison specifically. Differential flame graphs are quite new. We're still kind of tweaking how to visualize it correctly. And there are a few different implementations out there. The different people try different ways of actually using flame graphs to compare two profiles. Our option uses two flame graphs to represent the comparison of two profiles. We can call them test and baseline, or new and old, or whatever you want. So the first flame graph, the one you can see on the left here, so there's two flame graphs in the screenshot, is the actual differential. It kind of highlights the difference between the two profiles, and is drawn exactly like your test or new profile. So same shape, same sample counts. It's exactly the same shape as a regular flame graph. But it uses colors to highlight the difference from the baseline or your old profile. So blue frames mean less samples in the stack frame. Red frames mean more samples in that stack frame. So gray means no difference. And the darker the red, higher increase, like darker blue, higher decrease. The second flame graph, the one you see on the right, is what we call the elided flame graph, which kind of contains all the stack that were present in the baseline flame graph, so your old flame graph, but not in the new or test flame graph. So things that vanish basically from one, stacks that vanish from one to another. I know it's pretty confusing if you've never seen it before. It takes a bit of time to get used to. but it really proven to be a very useful tool. So it really allows us to easily identify regression and like easily compare two profiles and spot the differences very easily. And then obviously we can confirm that with regular flame graphs later. Regular flame graphs, as I mentioned, are great for analyzing code paths bottom up. Like reverse stack flame graphs are great for analyzing code paths top down. But sometimes you just want to focus on certain things in the middle, like libraries that are used in different code paths of the application, for example. So we created middle out merge, which allows users to select functions in the middle of the stack and kind of merge out of that, either top or bottom. So it can go both ways. Having a centralized profiler to mean that we can now provide an API for automation, like automatically profiling a new build during the deploy pipeline. Like if any regression is found, we can easily pinpoint the root cause with the differential flame graph. We can just compare with the previous build. Another very common use case is alerts. Let's say a CPU, a service had a CPU user alert. This would automatically trigger a CPU profile in FlameCommander. So the engineer, when the engineer receives the alert, like his page, he already has that profile to analyze. Saves time on bringing things back online. We also have a scheduled profile collection, like an hourly job that takes CPU profiles from random instance cluster, so we can create this historical archive of profile. It's really useful when you notice something changed, but it wasn't really caught during the build and the deploy process, and you don't know exactly what it is. So you can just choose a profile from a few hours ago or like whenever you want and compare with that to spot the difference, because we have that historical view. I'm also working with cloud-wide profiles now, which kind of is automatically collecting profiles from our whole infrastructure, so we can aggregate usage and find targets for improvement across the board, similar to what like the Google-wide profiling paper. And with that, I kind of want to wrap up this quick sort of high-level overview of FlameCommander and FlameScope with a few takeaways. So we really saw a lot of value in trying new visualizations, not just sticking with line charts and tables for everything. It makes finding and explaining things a lot easier, especially when we're talking about trickier products. Lowering the barrier of entry with abstractions and simple tools, especially for those without performance experience, made a huge difference in really scaling our efforts. A lot of people didn't have to come to us anymore. Having the centralized profiling tool also gave us more analysis options, like the cross-profile comparison, historical views, and so on. It also helped with discoverability. Right? Maybe an engineer went to FlameCommander to generate a heatmap, but ended up finding the memory allocation tool. So he now kind of knows two tools. Development cycles are faster too, because we can make improvements and have those available to all users. And finally, automation really allowed us to do things that just wouldn't be possible manually, like the cloud-wide analysis and tribal view and so on. And that's kind of all I had. I think I have a lot of time for questions now, I guess.
Yes, exactly. Thank you
Cool.
so much, Martin. So first of all, I'm going to enable the other pack members connected.
Sure.
If you have any questions, they could basically jump in. So I see that Mark is he's not on his desk. Joey, I will enable his webcam. Alejandro, let me try out, but I'm not sure if he's connected or not. No, he's not. All right, and I think there is, what else? Arinder is still there, so I'm going to enable him if he's up and connected. Yes, it is. All right, so first of all, I had a few questions. So you mentioned automation. So yeah. You show the capacity of comparing two flame graphs and highlighting the differences and so on. And I was wondering, say, instead of doing a visual representation of the differences, why don't you basically scan the two profile and just boom, say, okay, the main difference out there. This is the thing that you have changed to avoid someone that for example, that has never been touching flame graphs before, saying, "Oh, where do I start?" Basically,
Sure.
just to make things easier and I was thinking, if you do that from a pipeline perspective, then I was wondering what would be the output of that automation. How do you consume the output of the
Sure.
automation you mentioned? That would be pretty interesting to get more details on that.
Yeah, sure. I mean, we do have a kind of summary view that is more a bit text-based, especially for archival. We want to see that. And we do have that. It's pretty simple, fair table of changes, nothing too fancy. We did try different visualizations that kind of showed only the difference. So you see that a lot of stacks don't have any differences, so what's the point of actually showing them? We did try that, but we found out that it led users to kind of wrong assumptions. Because the way things are scaled, right? If I just show the difference, he sees, oh, this whole thing is different, and he might, end of the day, that might just be like, I don't know, 1-2% of the whole thing. So it might not be a huge change, but he kind of gets, even if I show 5% or I can actually show scales, it leads users to some like funky assumptions there. I remember we tried that and we had people, oh yeah, my application like he regressed so much, and then we actually did the comparison. It was not as much as you think. So we tried a few different visualizations and how people react to them, which is kind of tricky, especially if you don't have perfect experience. Like how do people? What's the first reaction people have when they look at those things? We're still like trying new things. The one other visualization we're trying for differentials, and it's really a tricky problem. It's no surprise that a lot of people tried that before on how to visualize those things. The two flame graphs where you kind of highlight and you can basically hover one flame graph and highlight the other where the change is. We tried that one too. We've been trying different things, but it's a tricky problem to make it very obvious to the user where the regressions or where the changes are.
Got it. And what is coming out from the automation? Is it you provided a dashboard, or it will be a link to FlameCommander of the output of the various check that you've done in the pipeline? Yeah. Okay.
So there are different things. If you're triggering the profiles, then basically what you get is a link to Flame. You can do the comparison via API too, but at the same time, the output is just a table, and it is not. Some users might find that useful, but what we see the most is that since the comparison is real time, I would just generate a link and they go to the UI and the comparisons that are available automatically. So most users would just go for the straight URL and go straight to the UI when they automating things.
Got it. And the other question that I had is when you mentioned the FlameScope with a different pattern, you explained the one single thread, the fact that it was waiting and all the stuff like this. And I said, yeah, basically you describe all the potential pattern. And I thought, hey, maybe you, instead of having this visualization that could be pretty fancy, and say maybe I'm pretty sure that they have the ability to detect those patterns and say, oh, and then just highlight that this is exactly that type of pattern. This is, you can see here, there's the thread blocking here, whatever. So basically, a way of guiding. And so I'm just thinking of guiding the user that consume that visualization.
Yeah, definitely. It's something we thought about. I did a couple. I'm not like a super expert ML engineer. I try a few like known models out there. We found a few things that the different phases are fairly easy to find. So it's something we need to experiment a bit more. With the stuff I managed to, and honestly, I probably spent like a couple of days on this only. Probably need to spend a bit more time on that. Is when I get a bit more time to try that, and I feel comfortable that we actually providing good hints that won't lead the users to like bad assumptions, then it's definitely something we're looking into. But it's a few patterns are easy to find, but a few others are kind of tricky too. Especially the wake ups ones, because they might change a lot. I mean, I show like 3 examples of the different like amount of time users the thread is actually doing work in the different sleeps, but I mean, the amount of different variations there can be quite big. Yes, of course, the most common would be like, I don't know, 100 millis of work plus sleep a second. And we might focus on those ones first, but like try to detect all of them is kind of, it can be tricky just because it's hard to find those profiles in the wild too.
And before I leave the space for the others, other questions is that it seems that you have millions of data there that you're dealing with. I guess you have a super huge storage because I think you're keeping track of all the previous traces and everything.
Mm-hmm.
To be able to compare. So I'm just do you have how many what is the storage for everything? I mean,
It's all S3, Amazon's S3. We didn't have like many issues with that. What actually simplifies the process too. Well, I think the only really issue that we run into the early versions of FlameCommander was the time to pull the profiles from S3. So we can actually process them in the UI. And that actually took a bit longer just because the raw output of profiles tend to be pretty verbose and huge. And that's why we migrated to the binary format I showed the Netflix profile one. So we migrated everything to that profile. It's binary, it's fairly easy to query and do whatever I want with that. And the size is actually pretty small at the end. Most of it because the stacks tend to be fairly consistent. So I can have just an index of different stacks, and then all my sampling, doesn't matter how long I actually run that, is basically just an array of all the stacks that I have. So we kind of compressed that a bit, and that helped a lot. So the binary problem. There are a few other binary formats around that are a bit compressed, but this one kind of worked pretty well for us for like both use cases of like tracing and also the sampling based one.
Got it. And I was expecting Joey, because Joey today presented his open source project, so like a unit performance testing on Python language, and we were speaking about visualization. So I would be interested, Joey. Do you think you could take advantage of that technology in your open source project?
Oh, definitely. First things first, Martin, your presentation is awesome. Really like I'm a big fan of the flame graphs. So I've used them at the client which I work to show developers, this is how your Java code is behaving. Let's see if we can improve it. And I have, for the average Java programmer that I've encountered at the client that I work at, it is a bit daunting to look at it first, because they get lost in access. It scares them a bit, but once they get through it, it's awesome. It's great. I love them a lot. So when I was building my little profiling library, I thought like I want to use those flame graphs too, but because of the time constraints, I wasn't able to really fit them in there because I really love them. So I ended up making some improvised flame graphs with Tableau to get that visualization, especially because I'm using Python's built-in C profiler to catch the statistics to show that. So seeing what you guys are doing, it's like light years away from what I cooked up a month. So it's really cool. I especially love the way how you visualize the CPU usage on that granularity. It's really impressive. It's really cool. Like
actually, one of the converters we have there is for the Python C profiler there. We have a certain number of users using Python in production here. So that's one of the converters we had to create. And once we move to, okay, let's just have this kind of intermediary format there, we just can keep creating converters to like whatever format we can capture around, and it worked really well. And I agree, like the first time you see a Flame is kind of downing, especially if you're looking at like the huge Java things with text that are 1,000 deep. It's kind of hard to understand, but once you get used to like what sort of thing you'd be looking at when you analyze that, I ended up finding it easier than the others like around. I mean, you could use the graphs that sort of like pprof uses. I mean, the standard one is like the tables that you can span with the hierarchy there. There's a bunch of different visualizations I mean, it's also like preference, right? And I know a lot of people like the graph one. I kind of like it for a few things. Yeah, on flame graphs, you can really have like loops there. I can't really go back to a specific function, which makes it harder, especially for node things where you have loops of things. So we've been thinking about adding graphs to. Oh well, it's preference too, and I think it varies a lot from language to language. Some languages are easier to visualize with a few things versus others, right?
Yeah, it's awesome. I'm smacking the C profiler results straight into a database. So I have all the results that usually comes out in the binary format of C profiler smacked into a SQL database, and then I can. My idea was once I have the basics of the framework nailed down, because I want to have a solid base, and then move on to create a GUI around it, which allows me to pull quickly and create those SFGs files that you also have, which you guys are also doing. And I love that idea. I actually got it from Brendan Gregg because I saw that blog and I was like, yeah, this is awesome. I want this.
Yeah.
But yeah, it's in the way that I am using FlameGraph. I'm using the profiler. It was a bit tricky to get the open source stuff that is available, like Brendan Gregg's FlameGraph generator, to get it to work in the way that I wanted to. So that was
the Perl script. Yeah, I don't think at least like most of the FlameGraph visualization development today is on. I think I'm doing that. I think Brendan I don't think he is changing anything on the old Perl script anymore. So most of it is in the JavaScript D3 thing. And that, I mean, it basically consumes a tree. Very simple. It's node, name, children, that's it.
Yeah.
It tends to be fairly simple as bits adjacent, and that's about it.
Yeah, I love it. It's great. It's amazing. Respect for you guys are great.
So here we go. You got something in your backlog, Joey.
For sure, more work.
Mark. Hey, Mark, how are you? Oh, we don't hear you. No. Oh, we don't hear you. Mark, Mark. Yeah, no. We don't hear you. While you're fixing that issue, Arinder, do you have any questions for Martin?
Couple of questions you've already asked, Martin. I'm just interested to see how, I mean, looking at the flame graphs and stuff, I'm looking how I can implement in more from the performance side of, let's say, response times from end user using a tool. How could I present that? I can leverage that. That's something I'm just, while I was watching it, I'm like, let's say if I'm using JMeter and stuff, threads running, how could I basically show it in that visualization?
Yeah, exactly. So the flame graphs are really useful when I get a stack out of things. So that's like when it comes in handy. And I did use it multiple times to visualize time too. So basically the aggregate sum of time in certain things. Instead of samples. Like samples are kind of similar to that, but I use for something called something, but instead of doing samples, I'm doing the actual like tracing points there, and that tends to wall time whenever that thing started and stopped running. And it worked fine well, but again, it end up making sense if you have a stack of something like that to visualize. I use for other weird things, but maybe not super appropriate, like navigation things. Sometimes I just want to visualize how much time each user is spending in each layer. Like he's going from this page to this page to this page to that page, and then I'm basically using the value of the samples to kind of represent the percentage of time he's going from one thing to the other. It works, but I mean there are like Sankey diagrams and other things that might be kind of appropriate for that sort of thing, I guess.
Yeah, it's like we go back onto this tornado graphs.
Oh yeah,
something using flames. Thinking
exactly.
how I can use flames.
Exactly. It is a tricky problem too, because like even if you figure out something that works and oh yeah, my mental model, like I can make sense of that. Again, we show you use it, and oh yeah, I don't really get that. Then you have to start all over. So we've been through, like with the differentials, we've been through the whole process a few times. Because like what, like for me and like the other perf engineers makes sense, like maybe it doesn't make sense for a node developer.
You're right. That's like we can come up with visualization which we understand. Sure, to someone else, like, what does it mean?
True. Yeah.
What am I looking at?
Yeah, exactly. It's a but it's an important problem to kind of focus on, especially in our case, like we have very few people to work on those problems. So like the more like developers can do their thing, better for us.
Yep. Plus, I'm more interested in the visualization side of things, in how we can, like, we started with just line graphs or histograms, but now we're getting to different kind of visualizations as a performance engineers, and see how far we can go with different kinds and what kind of information we can get out of them.
Yeah. I mean, I'm heavily inspired by Tufte, but that's my thing.
Yep.
So Mark,
That's it.
Mark has been reconnected. So Mark, do you have your mic enabled?
Yeah, testing 1, 2, 3.
Yeah.
Much better. Awesome.
Much better.
Thumbs up, Martin, and such excellent work. I was saying before, it's really nice to see the evolution of flame graphs turn into something bigger. I had two questions for you that made me think about stuff. One, sort of the alerting and threshold stuff. If I think about shifting right into SRE and other people that may not know everything there is about every instance, that there's nice things you can build on top of FlameCommander that at least start, like Henrik was saying, I like the some AI around or machine learning around those anti-pattern identifications. The visualization that came to me was like, I have the weather app on my phone, and it shows me like where the weather warning is and the projection, and sort of, you could even put sort of, you could put some forecasting into it, some predictability to say, we're seeing this pattern and here's where it's predicted to happen next. And that could be really interesting from a regression standpoint, but also a forecasting algorithm. The other thing I thought is, how do you find people using flame graphs to work back into the code base? And clicking on different layers or different components within the graph, and you're working back up into development. Is that something that, is there any development or direction going there, or how does that work, Bailey?
Sure, generally speaking, most people that tend to get the alerts and get those flame graphs are the people actually currently working on the code. So hopefully there's at least somewhere like familiar with the code base. But one thing we've been exploring is just basically tracebacks to the actual code base. So hey, I have a function here. Depending on the language, I feel we actually have line numbers, and we can pinpoint to that line specifically. Cool. Some we don't. The other thing we experimented is the kernel functions. Since we do like full system profiling, not just application level, we actually get the kernel stacks. So I can pinpoint it exactly to the kernel code. So things we experiment, but basically is deep linking to the code base itself there. That helped. It kind of makes it faster. But again, it wouldn't help an SRE that doesn't know the code base really well. Like they can get a hint, but like in our model, we never pay too much attention to, because we generally don't want our like overall SRE team that is not developing the code to be paged about like a specific application. Usually, it's just to the so that's
line 73. Go do something about it. Like that's not their
exactly. Exactly. We have a central SRE team, and their goal is more like generic issues. Say now Xbox Live is down, which is not related to a microservice. So that's why kind of the actual service goes to directly to the team. So that tends to work out well.
Cool.
And
awesome.
I had a question about what just Mark mentioned. So is there a way, for example, depending on the role of the user, for example, if I am a Python developer and I never touch about the kernel, are you, for example, removing the stack that doesn't make sense for the user itself?
Yeah.
Let's say, for example, I just want to see the Python stuff and I don't care about the kernel. So basically you're hiding the stack that won't be very useful for the Python developer, for example. Do you do that?
Yes. So in the actual Netflix profile, like repo there, we have what we call flavors, depending on programming language, or even like sometimes different ways of parsing the same programming language. And some of them abstract not just kernel code, they also abstract things that are not super interesting. Like when you check a stack of Java, you see a lot of interpreter. Like, that's not really useful for me. So we do like a lot of like playing around with the stacks to bring something a bit more meaningful to the user and something that he can translate to his code base more easy. The uninline one is a great like option because a lot of languages just inline a bunch of frames and the developer kind of loses track of like where he's like what's actually calling what, and that's why the uninline comes. So yeah, we do have a bunch of different options, but one thing we still need to do is kind of automatically detecting languages. Since we do instance-based things, we don't really know what's running there. And yes, we could like do some analysis, use some heuristics to find is this a Java app, is this a Node app, is this a Python app, and then kind of automatically select that for the user. Right now it's a bit manual, but at the same time, it does help a bit. So.
Is there no way to, for example, detecting the potential code of the app based on the container that hosts the code, for example?
Yeah, exactly. The problem is that most of the time we do system, like full system, basically full system profiles, and we have more stuff running there. We have container workload, but the bulk of it is instant, right? It's EC2, and then we might have an agent that is running a Java thing there, and I really want to see that because that might be the culprit of my problem. I want to see those things, so I want to see the whole thing, but so that's why it's trickier to figure out like what the application is because I'll have like multiple things running at the same time there too.
Awesome. Thank you so much,
Cool.
Martin. It was an amazing session. I really liked it.
Awesome.
So thank you to be part of this year virtual pack. That was great. So we have 5 minutes left. Do you have any last question for Martin, or should we take a small break?
I actually have one quick question for Martin, still alive. When are you triggered to look at the profiled results? So when do you go and look at it? When there's a problem, or?
Depends, like multiple use cases. Like, yes, the automation is usually when there's a problem with like we detected something, we took that automatically, and we need to kind of go and investigate. But a lot of the proactive improvements we do, like we use all those profiles too. We look at the large service and the main resource we're using here is CPU. Let's take a CPU profile. Let's see where we can cut things. So we actually use that to investigate issues that are corrective, not issues, but like actual improvements too. So like all sorts of use cases. We have a lot of different profilers too. Like applications are running out of memory. Hey, let's see where like what's actually allocating memory. We can profile all those things. And with BPF trace, we can like literally do anything.
Super interesting.
Cool.
All right. Thank you so much, Martin. Thanks for the session.
Thank you, guys. Thank you for inviting me in. Feel free to reach out.